So I have, in the last lecture and just now, I've just given you the basic definition of neural differential equations. I also told you about this link between NDEs and neural network architectures. And then I told you about kind of a state-of-the-art neural differential equation model, these coupled oscillatory RNNs to solve with high performance these kind of machine learning tasks. So now I'm going to spend the rest of the lecture talking about diffusion models. So who's heard of diffusion models before? Pretty much everyone. So who's actually used a diffusion model? Who's trained one? Okay, so two people. Okay, great. So I'm going to explain what a diffusion model is and how it's actually linked, or how it can be interpreted as a neural differential equation. And it's kind of interesting. So this is examples of outputs of some diffusion models. So who's heard of DALI or stable diffusion? Yeah, everyone. Okay, so you probably played around with it. This is now publicly available. These models, you basically type in a prompt, for example, like a chair that looks like a strawberry or something, I don't know. And these models will like imagine or just generate a random image that looks like that prompt, or is conditioned on that prompt. So they're generative models. They're models that take an input and maybe some random input as well, and then generate an image from that kind of conditional distribution. And they're super impressive. Like just over the last 5 years, there's been so much improvement in the quality of these generated images from these generative models. And kind of the generative model that's doing the best so far, or is the most popular at the moment, are these diffusion models. So what is diffusion? Can anyone tell me or give me a definition of what they think diffusion is? Yeah. Random movement of particles, yeah. What exactly happens though when particles are moving around randomly? Yeah. And diffuse. Yeah. So you've got it. So diffusion is just the movement of, it doesn't have to be particles. Actually, many processes in science can be thought of as diffusion processes. So let's just talk about particles for now. It's the movement of particles from regions of higher concentration to lower concentration. And it's just, this movement is just driven by the random motion of the particles, or random movement of the particles. Who's heard of Brownian motion? So this is an example of like random particles randomly colliding with each other and moving around kind of on a random walk in some space. Another example is like gas, for example, particles of gas. So say they're confined inside this box, and then we take out like one of the walls of the box and make the box bigger. Even though these particles are just randomly moving, they'll eventually start diffusing into the wider box. And so what you end up with a diffusion process is you go from some highly structured concentration to some uniform distribution. That's generally what happens in diffusion. So people also use diffusion to model other things, so energy, but also in finance, we can use diffusion models to model the evolution of stock prices. It's basically saying they evolve randomly from some initial time. So how is it used for images? So for these image models, these generative models that are using diffusion to produce images, it's just applying diffusion to an image. So what we do is we just start off with an image on the left here, and we just interpret that each pixel is like as a particle, if you like. And we're just going to let the pixel values themselves just do a random walk, like start randomly moving around and diffuse like that. Mathematically, that just means, or in most of the case, that means we'll just add some Gaussian noise to the pixels every time step of the evolution. And so we just start adding noise to this image, and what you find is whatever image you take, you'll end up with some generally simple distribution at the end. In this case, just a Gaussian distribution. So this is really interesting. This tells us that we can go very easily from an image to some noise, basically, at the end. And it's just a diffusion process that gets us there. Everyone with me so far? Yeah. Okay. So let's try and just define it a bit more mathematically, what this process of diffusion is when we're applying it to images. So we need to talk about probability distributions because diffusion is a random process. So we can just say that we start with some image here, which is drawn from some data distribution. So P naught of X. What does this mean? This just means it's just the probability of that image occurring naturally, like it's the probability distribution of natural images. If we sample from this distribution, we just get a natural image, if you like. That's the distribution that we would like to learn. And then we apply diffusion all the way down, and we can assume that our diffusion model is going to end us up at some very simple, well-defined distribution, say a Gaussian distribution over those pixels. This is our kind of we would call it a prior distribution here. And so we can model many different diffusion processes with stochastic differential equations. Who's learned about SDEs before, stochastic differential equations? Okay, so some people, not everyone. That's okay. So we can write this kind of diffusion process as this kind of equation here, where we say a small change in the image, in the pixel values, dx, is just some deterministic process. So you can imagine that maybe over time they just have a deterministic drift to them where their means just change slowly. So this is determined by this drift function. But then the interesting thing is we also add this small random noise to the image here. So we call this the diffusion kind of change. And what we just say is that this kind of random variable that we add to the images here, this W, is just a Wiener process, which can be a whole lecture by itself, just describing mathematically these kind of random processes. But for now, you can just think of it as adding Gaussian noise at each step, and G of T just tells you how much Gaussian noise we add, the kind of magnitude of that noise. Any questions on this equation? Does that make sense? No, it does. Yeah. Okay. Good. Yeah.
You mentioned this is a diffusion process. This is all mathematical speed of
yeah.
system.
Yeah. So this Wiener process describes like these particles as they randomly like change over time. And so that it's not a deterministic movement. You kind of have to sample this process to when you're forward simulating an SDE, you have to kind of sample many paths to create these distributions rather than just a deterministic path. So yeah, you have to define kind of how W evolves mathematically as like a probability distribution. You just say at some later time, the distribution is like a Gaussian distribution. So there's a super remarkable result, which was shown, I believe, by Anderson in the 1980s, that we can go the opposite direction. And so this is what we want to do. If we want to learn a diffusion model, which, given some random input, can produce a sample from our data distribution, basically give us a natural image. What we want to be able to do is to go from right to left. We want to take some prior distribution. We want to sample a Gaussian distribution and turn that into an image here. And this is a kind of a really remarkable result that says there is a corresponding stochastic differential equation that if we solve this differential equation, reverse in time. So if we start at xt and do time stepping from t to 0, we will end up with a sample from the initial distribution, from this data distribution. So I think this is a really remarkable result. It gives us a way to take some random image here and then just model it through this stochastic differential equation to end up with an image here. And what does this equation depend on? Well, it just depends on the stuff that we already know. So this kind of this drift function here and our diffusion function here. dW here is another Wiener process. It's just in reverse. So that, again, can be easily mathematically defined. And the other thing that it depends on, which is not in the original forward model, is this PT of X. So this is the probability of X, this kind of distribution of the images as a function of the time step. So at time equals t, the P of t is just this Gaussian distribution, and at P at 0, it's the data distribution. And at t equals t, it's somewhere in between. So I'm not going to go into how that's derived but it's definitely worth looking into and reading these papers to kind of understand why there is such a corresponding SDE for the reverse model. Now you can actually go one step further. It can also be shown that there's a corresponding ordinary differential equation, which if you do the same thing, if you solve this ODE backwards in time, starting from some sample of this prior distribution, so some random noise image, you will also end up with an x0 here that is drawn from, again, our data distribution, our P0 of x. So this is not a stochastic equation anymore. This is just a simple standard ODE, which is deterministic. So we give it a random image here, and it will give you a deterministic kind of sample from this initial distribution. So I think this is another really amazing result. This is shown in this Song paper, how to derive this ODE. And it looks very, very similar to this reverse SDE, so if we solve the reverse SDE, we get lots of samples. If we solve the ODE, we just get a single sample, but all of those samples are still samples from this initial distribution. And it looks very similar. So we have the drift term, we have the diffusion term, and we have the log of the density through time. Yeah. Yeah. So when you solve the SDE, imagine taking an increment of x, like you have xt here, and we have to discretize the SDE to solve it as we do normally. So you take one increment of x, you apply this thing, which is deterministic. But then when you apply the Wiener process, you have to sample like a random Gaussian noise that you'll add to the image. So you could do it once and just create one sample, and that would give you one path. But you could also, at each time step, you could also sample it many, many times and generate 10 samples for each time step. And then take those samples forwards to the next time step and like generate an exponential amount of samples that way. Whereas the ODE is just defining one path, like a deterministic path. But the cool result is that the ODE still gives, at the end of that path, it will still give you a sample drawn from this distribution. So it will still be a natural image. It's just a single natural image. Yeah.
AISE solve this reverse one is similar to the Black-Scholes model where you
Yeah.
can use the Beatles formula.
Yeah. Yeah. So the Black-Scholes model is very similar to this. So you can use similar kind of solvers as well, yeah. So how do we generate an image? So let me just write it step by step. So it's very simple. There's just two steps. We generate a random image, sampling each pixel from a Gaussian distribution. Or usually a Gaussian. So it depends on the SDE that you define, and the kind of final distribution that it evolves to. But often it's just a Gaussian. Then you just solve this ODE or the reverse SDE if you want, backwards from time t to time 0. And it's just a simple, we can use any ODE solver that we like that fits this equation. So this could be Euler, this could be Runge-Kutta, anything you like.
We have access to PDEs.
Yeah. Right. So you've just asked my question or answered my question. So what's the problem here? What do you think is the problem? Yeah. We don't know what PT of x is. This is like some super complicated function. Well, we know it here. We know that this is a Gaussian, but we don't know it anywhere else. This is a really complicated, probably never be able to express that analytically function. So what do you think we can do? How can we get around this? Yeah. Yeah.
Images.
Yeah. 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 So we're going to try and learn it. That's absolutely right. So the process of training a diffusion model is actually just the process of learning this distribution, this PT of x. But what we actually do is nearly that. We actually say we're going to learn this whole term here. So the gradient of the log of the probability. And we just approximate that whole term with a neural network. So that's the goal, is to train a neural network in some way, which I'm going to talk about later, so that it matches very closely this probability distribution, or at least we call it the score function. So what are the actual inputs and outputs of the network? Well, it's exactly the same as this right-hand side. So this right-hand side depends on the image and the time. So then the network is going to take X and T and produce some output. So what dimensionality output will that be, by the way? If the network takes in an image, what does it output? Or what's the dimensionality of the output? Just from this mathematical equation, what should it look like? Yeah. Yeah. Yeah, you got it. So this is the gradient of a scalar function. This is probably an image or a matrix. This is now a probability. It's a single value. This is a gradient with respect to X. So the output of S will just be another kind of image, or the shape of an image at least. Okay. So how can we learn that? Anyone got any ideas? Yeah. KL divergence measures the similarity between two probability distributions. So to be able to match your network to that, you'd have to have some data that you know is drawn from the ground truth distribution, which we can do here and here. But I guess we probably could do it here actually if we just do lots of forward sampling. So yeah, yeah. So I think that could work. Yeah, it's not how we've typically defined it, but that may be a different way. Yeah. Anyone else? Okay, so this is so one way. It's not the way that I'm going to describe next, but this is just a NOR ODE, right? Once we replace the score function with some neural network with some pre-parameters, this is exactly a NOR ODE that we've just been looking at. So how do we train these networks when we train NOR ODEs? Can anyone remind me? Yeah. Yeah, so we simulate it forwards and then match the outputs with respect to the inputs. So we know that if we simulate this diffusion process, we know what the outputs of the backwards solve should be, so we can match it to those outputs. So that's one way of doing it. The way that people actually do it is to use this type of loss function, where we just say that very simply, like even simpler, we want the network just to match, this the score of the probability distribution. So I'm not saying anything new, just to say I'm just trying to make sure that this is true. And we're just taking the L2 norm because this network outputs an image. That's the gradient of the distribution. And we want to make sure that this is true across all the inputs of the score function, right? So that we want to sample all the values of t and all the possible values of xt. Does that make sense as a simple kind of loss function? Okay, so again, I'm taking multiple steps at the same time here to give you the overview. But there is another paper you can read which says that this expectation over t and xt here can be rewritten as this expectation, where what we've done is we've turned the kind of unconditioned distribution as a function of x here into a conditional distribution of x given the initial value of x. So this is what's the probability of a noisy image given some initial noise distribution here. So yeah, you'll have to look at this paper to believe me that it's true, but this is a equivalent expectation. So now we define the probability of some x at some time given the kind of initial Gaussian value or initial prior image as the transition probability of the system. Okay, so let's just think of a really simple SDE. Let's forget about the drift terms and the diffusion function and just say that the diffusion of x is just exactly a Wiener process. And so I told you before, you can just think of a Wiener process as adding Gaussian noise at each time step, but it's kind of a continuous version of that. And the Wiener process actually tells us analytically what this transition probability is. It says, given some starting image here, the image at time t is just, some Gaussian Gaussian different, or it's the same image, but with some Gaussian noise added to it. This is the distribution. And the kind of magnitude of that Gaussian noise is just proportional to the time. So the standard deviation of the Gaussian noise just depends on how long the process has been evolving for. Can everyone kind of get the kind of high level concept, even though the math might not look too familiar? Yeah. So this is just an expression that we can take the gradient of with respect to x. It's very simple. You can derive it as this. That's very trivial to show. And so then if we just plug this transition probability into our kind of transform loss function, we just say that the loss now is just an expectation of the output of the score network. And we want to try and match it to 1/t times by x naught minus xt. So we're going to average this difference over all times, all possible initial random images, and then over all paths that that image takes. So all xt images. And if you just look at this in a bit more closely, like if you just think what we're trying to match the score network to, this is simply just the difference between our random noise and the image at time t. So what the score network is trying to do is just predict the noise that's been added to that image at time t. That's kind of just the interpretation of the loss. Okay, hopefully that kind of gives you the loss function that we often use to train these diffusion models. Any questions on this? I recommend going through this in your own time and trying to see if it makes sense mathematically. Okay, so here's the summary of diffusion models, and then I'll give you an example of how we use them in science. So how do we train a diffusion model? So first of all, there's 5 steps. First of all, you need to get lots and lots of examples of whatever image distribution you want to model. So these could just be many examples of natural images. Then you have to assume some underlying form of your stochastic differential equation that is defining that diffusion process as it evolves through time. And we need to understand what the transition probability is, what takes kind of the initial image here to some time t here. What's the transition probability of that happening? And then we define our loss function, just as I said before, and we can differentiate through this because we can analytically derive what this score value is. So we train the network, and then when we want to generate an image, then we just sample, or we solve this NOR ODE, or if we want the reverse stochastic differential equation, given that learned score function, backwards in time to be able to generate a new image. So we start from some random sample as the initial condition of this ODE, and then we solve it through time with like an Euler solver or whatever other type of discretized solver you like. So this review paper here, this by Yang, gives a really nice, goes a bit more into the math behind diffusion models if you want to learn more about that, and gives is a really good overview of all the different extensions of diffusion models and also their applications today. So I super recommend this paper if you want to learn more about these. Okay, any questions? Yeah.
In practice, what would this drift function
would
be recently in
yeah. So if I go to this example where we have like a stock, for example. So what this is showing is the random walk of a stock price if you sample it like 4 times or 5 times. So this is like solving the SDE forwards in time for a bunch of variables, for a bunch of instances. So the drift function, you can see here, if you look at the Gaussian distribution at the end, it's just the center is around 0. So what that drift function just does is define some deterministic drift that would otherwise end up, this Gaussian might like just drift upwards linearly, for example. And so that would just be a linear function here as a function of time.
And for images that?
Yeah, I'm not sure how to interpret that properly. Have a look at that review paper. It goes way more into the different choices that people make for these SDEs and the types of diffusion models that they produce. It's really, really interesting. Okay. So we're now going to think about using, I showed you at the start, diffusion models are the state of the art for image generation, like generative models for images. But people are also using diffusion models now to solve scientific problems. And so what I have is an example of diffusion model solving computed tomography. So everyone understands this, hopefully. We covered this when we were talking about hybrid methods at the start. So again, we have some sinogram that we observe from some image. So we scan ourselves. We want to produce one of these X-ray images, but what the device actually measures are these sinograms. It's the intensity at the screen. And so the goal is to do the inverse problem. Take this sinogram data and try and reconstruct the image or the absorption as a function of space here. Okay, so there was this paper that came out fairly recently from Song, where they used a diffusion model to generate these CT images. So you can, instead of learning the space of like natural images, now we want to learn to sample like medical images. So like images, images that would be output from CT scans. And you can imagine if I run like a million CT scans, I would have a good training data set, and I could train a diffusion model to generate new CT images from that training data, just using the process or the training algorithm that I just described. But the problem is, if I just train that diffusion model as it is, when I sample it, I'm just going to get a random image. At the moment, I don't have a way to like incorporate the sinogram into this workflow so that it doesn't just produce a random image, it actually produces the image that I want, the result of the inverse problem. So can anyone think of a way that we would incorporate our sinogram into this workflow to help the diffusion model like come up with an image that solves the problem? What we're trying to do is create a condition distribution here. We're trying to condition our diffusion model on some observed data to make an image that is like the solution. Any ideas? Well, how could you use this diffusion model in a traditional inverse algorithm as well? Like, how could you use it? Yeah.
I guess the image that you're generating compared probably to the original image.
Yeah.
That is present in the data set, and probably add that as a constraint.
Yeah. Yeah, I see what you mean. So yeah, you're kind of on the right track. So I'll tell you, because it's not obvious how to do this actually. So what they did is, again, this is just let's just assume that we've trained that diffusion model. So it generates, given some random noise, it generates a CT image that is in the right distribution of CT images that we know the image lives in. So yeah, again, once we train that model, we can just sample it just in the process exactly as I described. And this is the kind of code that does it. You just generate a random image, and then you solve this normal ODE in reverse, where you have this trained score network function that we've pre-trained. So what this paper suggested is doing a very simple extra step inside of that ODE solver. And it says, as we solve this ODE solver 3 times, so as we slowly turn this noisy image into the final image, at each time step that we're doing that, we add this extra update to the image on top of the update that removes the noise from the image. So this is it's called a proximal optimization step. That's a very kind of fancy phrase. And there's a whole theory of like proximal optimization theory, which I'm not going to get into, but what you can think of at the highest level is this optimization step is just trying to nudge the image closer to the solution of the inverse problem. And what it does is it just says, okay, given the current image at time step t, I want to update the image so that the loss of the inverse problem. So if I do a forward simulation of that image to produce an expected sinogram, I should try and minimize the difference between that expected sinogram and the observational data that I have. So you could also think of this as a loose level, taking like a gradient step in the direction of the loss function of the inverse problem. So it tries to push the image so that it satisfies the observational data, and then carries on reverse diffusing the image to eventually end up with an image that satisfies the inverse problem at the same time. Okay, so that's probably fairly complex, but do you get the high level kind of idea?
Each point in time,
yeah,
we have a observation and get noise.
Yeah. Yes.
And at each point in time,
yeah,
we do a forward. I mean, we try to find the sinogram of
Yeah.
that image.
Yes.
And that matching wall, we know it's to be the right thing.
Yes.
And that gradient with respect to that should
yes,
push up.
yes,
Doesn't move the right direction.
exactly, yeah. So what we're doing is we're like interleaving a kind of gradient descent algorithm to update the image, just like we talked about before. We were doing gradient descent on the image to update it to match the sinogram. But at the same time, we're also adding diffusion. We're assuming our initial image is a Gaussian, and at the same time, we're like adding a reverse diffusion into that image to like help it, give it a prior. Basically, it's guiding the image to like the image distribution that we know of. So it's really a really cool method. It like interleaves kind of standard optimization with a diffusion model as the prior. So yeah.
And then during evaluation time.
Evaluation time. What do you mean?
I wouldn't have labeled with log.
So so when you do a new scan, you will always generate a new sinogram. So you always have this label in this observed data that you're trying to match to when you're updating the image. Yeah. So it's actually really cool because this doesn't depend on the observational setup of the scan. You just compute the gradient. No matter what the observational setup is, you can still get a gradient of that. So it's kind of independent to that. So, I mean, here's some plots from that paper. It's just comparing this kind of optimization interleaved with diffusion model method with some other kind of state-of-the-art methods, like using GANs as your prior for your images, and more traditional total variation method as well. And yeah, at least on the data sets that they show in the paper, it seems to be a very competitive algorithm for learning these CT image reconstruction problems. Okay, so I need to stop there. So NDEs use neural networks to represent learnable parts of the equation. Discretized NDE solvers can be thought of as neural network architectures with interpretable dynamics, and it provides this really fascinating link. And many state-of-the-art models like diffusion models, co-RNNs, can be interpreted as NDEs, and it's really interesting to study them. So thank you very much. I'll see you on Wednesday next week. Yeah, see you then.